Okay, for the archivability proof of the interference channel, we need again superposition coding. So we again have cloud centers and we have satellite. The coding scheme was developed by Carlyle in 1978. The decoding scheme is due to Han and Kobayashi. So for the coding, there's a new idea now. We split the two messages, W1 and W2, into two independent parts, W1 prime and W12 prime, and W2 prime and W22 prime. And WK prime and WK2 prime have the rates R prime K and R2 prime K for K equal 1 and 2. And now the idea is that the receiver 1 not only decodes W1, which corresponds to W1 prime and W12 prime, he also decodes W2 prime. And you will see this helps us. Later he throws away this part here, but it helps us in achieving better rates. The same is done for receiver 2. He decodes W2, but not only W2, he decodes also W2 prime, W22 prime, that's his W2, and W1 prime, which he later throws away. And as I told you, we use superposition coding, as you see here in the picture, and introduce, as usual, two random variables U1 and U2 to generate codebooks for the messages W1 prime and W2 prime, respectively. And the codebook for transmitter 1, you see here in this picture, you see here this superposition coding. And as I told you before, we consider the distribution, a joint distribution of U1, U2, X1, X2, Y1, and Y2 that factors in this way PU1, X1, PU2, X2, and then the channel which goes from X1, X2 to Y1, Y2. How is the code construction now? So first we consider transmitter 1 and PU1. Again, this U1 denotes the alphabet of this random variable U1. We generate 2 to the n R1 code words from W1 prime to 2 to the n R1 prime by choosing the U1I W1 prime independently PU1, this probability distribution here, as we do it every time, a lot of times before for each symbol in the codebook. And for each U1 to the n of W1 prime, we generate now 2 to the n R1 prime code words of X1n W1 prime, W12 prime, where W12 prime goes from 1 to 2 to 2 to the n R12 prime. You see, these are again now the satellites of this cloud center here. And by choosing this X1I independently again using PX1 under the condition U1, so that's a channel from U1 to X1 somehow for I equal 1 to n. And in a similar way, we generate for encoder 2 or transmitter 2 U2 to n, this codebook here of W1 prime, and choose then this cloud center X2n, W2 prime, and W22 prime for transmitter 2. This is again the cloud center, and this is the satellite somehow. And now the encoder, when he has given W1, which consists of W1 prime and W12 prime, he transmits X1 to the n of W1 prime and W2 prime. The same is done by the second encoder. Given W2, he transmits X2 to the n of W2 prime and W2 prime prime. Now the decoder is given some Y1 to the n, so decoder 1, And he tries to find now this triple W1 prime, so tilde of W1 prime, tilde of W12 prime, and the extra thing here is also tilde W2 prime, such that this is jointly typical, concerning the joint distribution of U1, X1, U2, and Y1. And if one or more such triple is found, then choose one, and we call it the estimate of W1 prime, W12 prime, and the estimate of W2 prime. If no such triple is found, then it's somehow an error, and we put all messages equal to 1. And decoder 2 proceeds as decoder 1, only we replace 1 by 2 and 2 by 1 here. Now we have to do the analysis. And because we do so many analyses, I also will give you the idea again. So the idea starts with this, with probability 1. We will have that the thing is typical and everything is fine. Not everything. Now we have to look at what kind of errors can happen. So we look at this triple W1 prime, W12 prime, and W2 prime. And now the remaining analysis is similar for that of the degraded Bloss-Cut channel, with an important exception. Receiver 1 is interested only correctly decoding W1 prime and W12 prime, and not W2 prime. So this event doesn't matter. If this event is wrong, it doesn't matter, because his goal is only to receive correctly W1. That means that the event that W1 prime is, the estimate of W1 prime is correct, the estimate of W12 prime is correct, and the estimate of W2 prime is not correct, is not an error, and this can occur. We thus can split the error probability into 6 disjoint events, so we leave out this event here, that correspond to the 6 interesting events, a way in which one or more of the W1 prime and W12 prime and W2 prime is incorrect. So doing this, so we follow our typical analysis. So I think you should be used to this. And doing this, we get this result here, only for these 6 events. And we combine both bounds with those for receiver 2, again 6 events. And then this R of PU1 and PU2X2 is a set of non-negative pairs, R1, R2, that satisfies all these bounds we have, where, of course, R1 prime and R2 prime are greater or equal to 0. And this factors out in this way. Then it turns out that the following set is contained in the capacity region of the interference channel. It's just the union over all PUX and PUY we can choose of this rate region here. This is a rate region we get with our methods, or we learned now, and with a special extra thing that we not only want to have W1 hat, an estimate of W1 hat, we also want some part of the second. We try to analyze also some part of the second, of this other message, perhaps it's better to say. We can simplify this. I think in the script you see a way you can do simplifying this. There, all single steps are given how to come from the previous region with R1 prime and R2 prime, and we want to get rid of them, and we get exactly this rate region here. This is known as the rate region of Hahn and Kobayashi. And the proof you find in the script is to make it easier is from Kramer of 2006.